Okay, welcome everyone to the AQT colloquium. It is a pleasure to have Xinran Lee. He's a Chamberlain postdoctoral fellow at Lawrence Berkeley Lab. He's been here for about 3 years. He did his PhD at Princeton University, where he worked on dark matter searches using liquid argon detectors. And then since coming to Lawrence Berkeley Lab, he's been still doing dark matter searches, but now using superconducting based detectors. And the title of his talk is on the screen, and I leave you with Xinran. Take it away.
Thank you. Thanks for the introduction, and thanks everyone for joining. Today I'm going to talk about the synergies in low mass dark matter search and quantum sensing. So this is the quest for more sensitive detectors and better qubits. It's a long title, which means my talk will be short, relatively. So I do want hear discussions and questions. This is really a good opportunity for me to learn from the quantum side as well. Okay, so starting from a background, let me introduce what is dark matter and why we care about it. We see evidences of dark matter exist in the universe from multiple different ways. Like, for example, we observe the cosmic microwave background and see the footprint of dark matter interact with normal matter in the early universe when the universe cool down and expanding. So we saw it from the CMB. We also saw it on the galaxy rotation curves, which is shown on the top right here. If we just assume the amount of mass seen by the light, the rotation speed outside the further away in the galaxy is too fast. So that there must be some mass in addition to the visible matter. Or we like other strange galaxies, like two galaxies collide with each other, and they generate the different distribution in their visible mass matter and then the gravitational mass center. So that is also a really direct indication of something that gravitationally interact with the other matters, but can't be seen by light. So what are they? They all point to some existence of dark matter. But does dark matter interact only through gravity, or can it be? Can there be other interactions? So that's the answer we want to ask. That's the question we want to ask. But before that, the different models of dark matter, they can be very light, or say wave-like dark matter. They just like light waves. So that's not the topic today. Today we're talking about the dark matter mass in the range of EV to TeV scale, which is the similar scale to normal matters, and they interact with normal matter through scattering or beam absorption. So that is the topic we're talking about today. Of course, like the wave-like dark matter, for example, axions, if you heard of the name, it's also a very closely related topic to quantum sensing, but that's not covered today. Okay, so on the EV to TeV scale, dark matter direct detection, how do we do that? We can't see dark matters, but we hope there is some interaction between the dark matter and normal matter. So we will have a target sitting there and waiting for the dark matter coming from the universe. Goes through the Earth and hit target, and then leave some energies behind. So that is how we detect. It can be a scatter, which it goes out but leaves some energy, or it's being absorbed. So it deposits the whole all of its mass as energy. Then the mass will propagate. So the energy will propagate inside the target and finally being collected by some kind of sensor. So depending on the different type of target and different type of sensing technology, you're actually looking for different energy carriers. It can be charged, it can be light, and it can also be photon. Phonon. Yeah, so and finally, we do statistical analysis and trying to look for excessive signal rates above the environmental background, the estimated environmental background rate. So because dark matters are rarely interacting with normal matter, so this the chance we see a signal is very low. We do want to reject all the other background, for example, cosmic rays and environmental rejected background by putting a large shield around our detector. So what is a good dark matter? It's good to look at this. It's a summary of all the current results of the dark matter direct search. On the x-axis, we usually plot it as the dark matter mass. And as I said, we're looking for like if there's a keV to TeV scale. And on the y-axis, this is the dark matter to normal matter interacting cross-section. And this is just how strongly dark matter interacts with normal matter. The lower you go, the weaker is the interaction. So here, this pink region is excluded by the current experiment, but there's still a huge space in the lower left corner. And we want to push to this corner. How do we do that? So pushing to the left, we need to go to look at lower dark matter mass. That is why in the title I said we're looking for low mass dark matter. And we need the detector with low threshold. I'll talk about this later. And on this corner, we're already doing really well. If you look at this, is like more than 15 orders of magnitude, and we do need the huge detectors. This is another story. But and then for both of them, if you want to push that diagonally, you need lower background, and this means clean material, no radio background, and the underground labs, but also much more. And this is the more is we're going to talk about today. So yes, we're going to look for lower mass range. First of all, it's very interesting in terms of physics. We have a lot more dark matter candidates falls in this mass range, and also it's a new parameter space. We can start with small detectors. We don't need to go to huge detectors, so that's also very interesting. And a lot of different technologies applies to this targets. And from this top plot, you can see, so this is the plot of the dark matter mass versus the energy it deposits inside of targets. And this box, I use this red box to search out the regions we are interested in this talk. You see that as you go low in dark matter mass, because it's just simply lighter, it will deposit less energy in the target. So you quickly goes below, say, 1 eV, and your detector needs to be very sensitive. You need to be sensitive to less than 1 eV energy. That means for the energy carriers of charge or photon, it just doesn't excite anything. Like you cannot ionize any charge from a semiconductor with less than 1 eV energy. Say in silicon, it's like 2 eV band gap. Same for the photons. Then we can only rely on phonons. So that and actually the phonon has a continuum spectrum all the way to 0. So that's great. Phonon is the natural targeting energy carrier we're going after for this lower energy and lower dark matter mass. So we need the phonon sensors. And interestingly, although we call ourselves high energy physics, but the phonons, this is condensed matter energy scale, and we are learning a lot from the condensed matter side. Okay, so this is what the phonon signal looks like in the example. The common example is the silicon target. On the left is the signal energy spectrum from a 10 MeV, a mega EV dark matter. On the right is from 100 mega EV dark matter. So first, you can notice as you go low in mass, the event rate. So on the y-axis, the event rate expected in like per kilogram target mass per year per EV. The event rate goes up like 2 orders of magnitude. So this is simply because we have the same energy density of dark matter around the Earth. You have lower mass per particle, you have more number density. This is the first reason. And the second reason, is because the small energies, the spectrum is compressed to the low energy end, so you get a great boost in the event rate. So that's great. So if you can really push the detector threshold to a lower, you gain a lot from this rise in the speed rise in the spectrum. And then also, if you are sensitive to this hundreds of milli-eV scale, you start to see this enhancement from the collective interaction of the crystal lattice to dark matters. The purple dashed line here is the simple like two-body collision energy transfer, and the blue is the same is the energy transfer from the same dark matter but on a lattice, silicon lattice. You get this boost because of the phonon mode. So that's all that combined together. You can look at this plot. This is a nice demonstration. If you go from 1 EV threshold to 1 milli EV threshold, you can gain a huge amount of phase space here. So that is very exciting, and this is why we are pushing for a low threshold detector. But on the other hand, if we are looking for phonon, of course, this is a double-sided double coin. For us, this is good signal. It's great. But for quantum people, this is a problem. So you must have heard this observation from the Google Synchron processor. They say they saw this randomly appeared catastrophic whole chip error burst once every like tens of minutes or hours. And they say this is because cosmic muon penetrating the chip, depositing a burst of phonons. They propagate everywhere and disturb all the qubits. And you can see after the time the muon hits, the error rate shoots up and then slowly comes back, recovers. And for us, we saw this type of positive. Oh, this is like what we want to see. If it's not the muon but dark matter, this is great for us. We're looking at we're detecting something with a quantum chip. All right, so same story here. Really, the two fields are closely related. So for us, we want to detect these signals. For the quantum world, you want to reject this disturbance. Okay, so of course, since I'm from dark matter, let me start from the dark matter detection. We want to look for phonons. We want to look and specifically we're looking at athermal phonons, meaning the higher energy phonons that's higher than the thermal phonon distribution. And we use the fact that they break Kufu pairs in superconductors to look for them. So we look for superconducting devices. For example, the TESs. I'm from the Tesseract collaboration, and we have two detectors. One is called Herald, the other called Spice. Altogether, we call ourselves the Tesseract collaboration. And in the middle, this is another type of device called the kinetic inductance device, so called KID. And this is an example from Italy group. They're using aluminum KID, shown in the picture here. Or you can directly use qubit. This is very interesting here. This is proposed by our former student in our collaboration, now at a postdoc at the Los Alamos National Laboratory. He called this device SQUAD. Okay, I'll start from the TES. For TESs, what is it? TES is transition sensors. Basically, we run a DC current through a small piece of superconductor. And through the Joule heating of the superconductor itself, it can hold its temperature at the critical temperature. And we cool the bus temperature far below the critical temperature. Then, because of the Joule heating, it just stabilizes itself on this transition edge. So it's called the transition edge sensor. And because of the sharpness of the resistance and temperature dependence, a small temperature change will transfer to a large resistance change. And if we use constant voltage bias, this resistance change translates to a current change and can be sensed by sensitive current sensors, for example, squeeze. So this is the basic idea. And of course, for energy injection, the energy translates to temperature by dividing, you divide the energy by the heat capacity. The heat capacity is proportional first to the critical temperature of your superconductor, and also proportional to the total volume of your superconductor. So that means if you can reduce the superconductor, the TES volume, you can gain a lot on this sensitivity and also gain a lot on this energy resolution. So that's why here, this is our state-of-art device on a silicon chip, and we only have 0.25% instrumented area on top of this small silicon chip. Yeah, you can see this small dots. These are the individual TESs. The reason is because we want to reduce the heat capacity. Not only we reduce the area, we also use the technique called quasi-particle trapping. So here, this is on the right. This is a demonstration. First, we let the asymmetrical phonon propagate, bouncing around in the chip until it hits our device, our sensor. And our sensor actually has two components. First, there has a large area of phonon collection fin, and it's made of aluminum. It's directly coupled in good contact with the actual TES, which is tungsten. And the tungsten is much smaller in volume and thinner as well. So the idea is after the phonon creates quasi-particle, breaks Schofield pairs creates quasi-particle, it starts at this higher energy level because of the higher TC of the aluminum. Then it thermally diffuses, and once it reaches this region where it overlaps, it has the proximity effect. The TC slowly drops to the TC of the tungsten, which is around 15 millikelvin. So in this dropping process, the quasi-particles loses energy and it won't come back. So all the quasi-particles created in the aluminum will eventually be trapped into the tungsten. And in this way, we can concentrate our signal in a smaller volume that drastically increase our sensitivity and lower the energy threshold. Okay, so this is the state of art for TESs. And then let me talk about the kinetic inductance device. So this is more of a newcomer in the phonon detection world. Heats are normally used for photon detections, especially in cosmic microwave background experiments. But for us, if we want to go to larger detectors with larger mass, we need multiple channels, and the heat, they are resonators, so it's very easy to multiplexing. So this is a natural choice for the next generation superconducting dark matter detectors. How it works, similar idea, but this is a resonator and RF frequency device, not DC. So you have a resonator, and the resonator has the inductance of the resonator has two parts. One is the geometric inductance, and the second is because of the kinetic inductance of the superconductors. And the kinetic inductance of the superconductor actually changes. It depends on the quasi-particle density inside it. So if you have some energy injection, Schofield pair creates more quasi-particle, the kinetic inductance will change, and you will see your RF transmission change. So that is, we call it the S21 signal. You see the signal both on the amplitude and also on the phase. We call the amplitude we call it the dissipative signal, and the phase signal. So same idea here, because what matters is the quasi-particle density. So naturally you want a smaller inductor in the resonator, like physically smaller inductor. You want it thinner in thickness and thinner in width. So it gives you higher clamping and a higher sensitivity. But if you consider how the phonons are propagating, it actually bounces around multiple times before it reaches your superconducting films. And because this is a RF circuit, you not only have the inductor, you also need to build the capacitors. Usually the capacitor takes up much more space than the inductor. And you also need to have your RF feed line and the whole, like to ensure good RF properties, you usually have a full ground plane on the chip. So everything else can absorb phonon as well, and it's actually not active, so your phonon will get lost. Only the phonon hitting the small inductor can generate the signal. This is a big problem in the KID application. So that's why KID is more of a newcomer in this game, and we're actively working on it. One natural idea, of course, is first, what we can do is to remove the ground plane. Like for example, this is the device we're running here in the lab. We can remove most of the ground plane and leaving only a narrow coplanar waveguide as the RF feed line. And here you see we have 6 resonators hanging on the feed line. We shine it with 60 keV gamma source. And this is what we saw on the leftmost and rightmost channel. We only detect about like 2 keV on the right channel and like 200 eV on the right channel. And this scales nicely with the area of the inductor. Yeah, this is simply because you have all the other areas. Although I removed the ground plane, you still have the area from feed line. This is still a small fraction. You saw this big loss, and you see this is see the phonon loss from the feature that this correlated the energy dependence has this curvature. If there's no loss, then you should see a straight line of the energy sharing between the two channels. And in contrast, this is what we saw in our state-of-art TES device. This is much more sensitive, so we are calibrating it with optical photon instead of gammas. And we saw this single photons here and here, single photon, double photon. And first of all, you don't see a spread in because of position dependence. This is because the small coverage fraction and phonons really propagate multiple times, bouncing around multiple times, and it's uniform. So it's a 50-50 energy share between the two channels without position dependence. And second, so this is why you don't see this mirroring, and that also you don't see any significant phonon loss. And we can do that because on top of this small coverage area, the inactive area is even smaller. So we can allow the phonon to propagate and bounce multiple times before it reach the active area. And we cannot do it for KID. So one natural solution is we do similar things for KID, right? We also have this aluminum phonon absorber and using quasi-particle trapping. So this is a prototype device I made, but it's not working. We're trying to understand why. To do so, we need a superconductor that has lower TC than the aluminum. There's a specific reason why the collector has to be aluminum, mainly because the quasi-particle lifetime in aluminum is like 3 orders of magnitude higher than the other common superconductors. So we are looking for some resonator material have much lower TC than aluminum, and the hafnium is our choice. So we Toki Suzuki, he's the PI here, and he figured that the hafnium is a really good material with tunable TC with heated sputter deposition. You can tune the TC of hafnium in the range from 150 to 400 millikelvin. So here is an example resonator we built. This is 250 millikelvin, much less than the aluminum TC, so for screw trapping. It's because of the low TC, it has to run at a lower frequency. So it's around 2 gigahertz, and we achieve the internal Q out higher than 10 to the fifth. And also, mentioned the kinetic inactance of the hafnium film is quite high. So it's really a promising material and a promising device. And now we're looking for the R&D of the hafnium aluminum interface to ensure good quasi-particle transportation between the interface. Okay, so this is the story for kids. And finally, maybe it's most interesting for you guys, this is the qubit. This is the squad proposed by Caleb Fink, and here's how it works. So as I said, you can create cool pairs in this aluminum trapping, aluminum collector, and trap quasi-particles into TS or TS, or you can trap quasi-particles into a junction. So this is a really bad qubit, but you can use it to detect dark matter. After you trap the quasi-particles, what happens is, depending on the number of odd or even number of the quasi-particles, you see the resonant frequency jump back and forth on this qubit. And in the time domain, you will see a trace like this. So once there's a tunneling of a quasi-particle, you see a jump. So this jumping rate really depends on what is the quasi-particle density on your junction, or say on the island. And here they simulate a pulse of a quasi-particle pulse. And here this is a time domain trace, and you start with a huge amount of fast jumping and it slows down. So we are looking for this feature. You can look for this feature on the baseline and use it to look for dark matter. This is a really nice picture, and with it, you can really achieve 1 millieV threshold. Basically, this is only limited by the superconducting band gap, which is, it can go much lower than this as well. So here are the numbers. We already achieved around 300 millieV RMS in this device. And this KEEP device, this is more or less the leading results from this group. It's 24 EV. It's far behind the TSs because of the phonon collection efficiency problem. And of course, this qubit is only a proposal, but we are very interested in looking forward to the result. So of course, as I said, you can keep going into smaller volumes, keep going to lower TCs, and try to improve the Android resolution. It seems all really good, but is that really the whole story? The answer is no. There are some troubles behind the scenes. As we go lower in temperature, lower in energy threshold in the TSs, we saw this a huge amount of background. We call it low energy excess events, or say like microfractures. What we figured out, this is a nice paper put out by a student in our group. If we glue the chip down onto the copper holder, because of thermal contraction, after we cool down, there is microfractures and releasing this small amount of energies randomly. So you see a huge amount of events. This is a red curve comparing to the device on the left, which is hanging there freely by aluminum wire bonds. So this is minimum stress. So this is the red versus blue. You see this a huge amount of events introduced by simply because of the thermal contraction and the stress. We know this is not dark matter because we saw this event rate go down exponentially over time. So of course, this time dependence tells us this is not dark matter, but some kind of background. And even even without gluing and only with this wire hanging, you still have the stress between your metal fumes and the crystal. After you cool it down, the stress builds up. Well, since your deposition, the stress is built up, and then it releases. So that's it's a non-avoidable problem. And the more fundamentally, it not only shows up as individual pulses, but below your energy threshold, it shows up as short noise. So you can see this, your noise spectrum becomes better and better over a course of say 2 weeks. So this is on one hand, we can wait long enough until this decays away to achieve a better energy resolution. But on the other hand, the decay is quite slow. We do want to have some thing that is lower stress. So this is what we are doing right now with our collaborators at the Oregon National Laboratory. We are looking into this iridium platinum bilayer material, which also offers us the low TC as the tungsten we are using, but also it demonstrates much lower stress. So hopefully we can get a device with much less microfracture background in the TESs. But for keys and qubits, this another story. Usually for a good RF resonator and the high kinetic inductance, the price of materials are limited. So what we can do, and this is we're talking about like the really coming to the key points here. We're trying to do phonon engineering here. So the first thing we can do is we can coat some reflective coating to guide and prevent phonon hit some parts of the detector. So this is the PhonoNext project. We have some collaborators on the call as well. And this DOE accelerator funded the project. And then I also want to mention this really cool paper put out by ALP recently. And basically, you can also use 2D structures to do the phonon engineering as well. So first, starting from the phonon reflective coating. First question to ask: which are the phonons reaching our detector? So phonon they propagate, they also decay. The decay rate is actually pretty fast for the high energy asymmetrical phonons, and then the decay rate decreases as the phonon energy decreases, and finally they reach more or less a free streaming state. You can consider different types of phonon decay. It can decay on the surface. It can go on harmonic scattering. It can also decay on the isotopic impurities in your crystals. So you start from an initial distribution at high energies, and then slowly approaching this thermal distribution. So we want to understand how phonons propagate and where on the spectrum do we stand when we build a detector. And so then we know what are the phonon energies we're going after. So this is the calculation by Schneid in our group. He did the DFT calculation that shows the different decay mode and lifetimes of different types of phonons. Overlay on top of it, I can draw a line here for a typical phonon collection time in 1 millimeter by 1 centimeter square detector, and look for what is the energy scale here. So from usually like hundreds of microseconds, the phonons will all decay into this 0.5 to 1 milli EV range, or say 1 to 200 gigahertz phonons. So the answer is yes, we want to protect or preserve. So for dark matter detection, we want to preserve the phonons in this energy range. And this is, of course, above the aluminum superconducting band gap. So we want to preserve the phonons in this energy range. So what we can do is we just design a multi-layer structure that opens a gap in this frequency range and reflects photons reflex phonons. So we can put this coating everywhere below the superconductor other than this active superconductor region, which is the inductor. So the phonon will reflect off everything else, but only collected by the inductor. So we already demonstrate the technology by for around 6 gigahertz frequency range with the silicon germanium bilayer. This is validated by the infrared optical response measurement, and it matches well with the simulation. We also, this is Eric from in our collaboration from the Center of X-ray Optics. He also demonstrates this terahertz region. We use the silicon and the molybdenum bilayer, and this is a much smaller scale, so on the less than 10 nanometers, to targeting the terahertz phonons or X-rays as our photons. So for 100 and 200 gigahertz, we're just looking for something in between. We have the designs ready, and we will fabricate device, and hopefully we will see this curved distribution go up and go to a straight line. So we'll have this device ready for test soon. Okay, and on the other hand, this is also very interesting. I want to talk about. We can also do this two-dimensional phonon lattice to protect the qubit and also protect to use it for the dark matter detector. But because of the feature size, here we're talking about a few gigahertz range. This is far below the aluminum band gap. It cannot create a cool pair. But there's another problem related here. This is the two-level system noise. We know two-level system noise will cause incoherence in qubits. For dark matter detectors, this is also a significant source of noise in kids. So what they do here is they can use this 2D lattice to open up a gap around the around 6 gigahertz. So the two-level system noise will saturate easily in this frequency range. Then, if you tune your qubit into this or into this gap or above it, you will see the two-level system noise saturate, and it no longer cause your qubit to be coherent. So you will see this increase of the coherent qubit lifetime once you go above this frequency, which is shown on the bottom plot, and on top plot, this color of this point shows the contribution of the decoherence from two-level system noise. So after you go above it, the contribution from two-level system noise drops. The points are blue, and the lifetime goes up because they are above the gap and they saturate. So this is very nice, and basically you can do this to enhance the qubit lifetime by like a factor of 2 or so. On the detector side, we also struggle with this two-level system noise. For example, this is on the left. This is the typical noise spectrum from aluminum kit. The dashed lines is the phase readout, and the light blue is the two-level system noise, which is the pure phase noise. And of course, when you say why not you use the other readout channel, which is the dissipative readout, it's the solid line. It seems to have much less noise, but the signal is also much weaker on this direction. So here on the right, this is IQ plot for say the S21 plan for the signal. The signal goes this trace, so it has a much stronger component on the phase versus on the on the radio direction, which is the dissipative direction. So once so that's and this noise blob shows that the two-level system noise causes this phase direction much higher noise than the distributed direction. So what we can do about it? Usually people go to larger inductors, and it is not feasible for dark matter because it increases more passive area. Or people go to higher RF power to make the 12 systems saturate, and this can be seen on the red plot. This is also not it's not feasible for us because we want to use low TCTs and they saturate easily before the 12 system noise 12 systems saturate. So maybe we can try to remove the 12 systems from the resonators by doing some like buffered oxide etching or cap layer coating, but this is needs some significant R&D effort. One thing we can do for sure is lower the resonant frequency. That's another reason why we look at 1 to 2 gigahertz. But of course, here this phonon engineering idea is coming to rescue. We can try to block the 6 gigahertz or lower phonons and make the TLS saturates much faster, then we can avoid the TLS noise. And of course, this is not related to phonon, but we can bypass it by using some quantum limited amplifiers and use the dissipative signal readout. So basically, we are lowering the amplifier noise here. So one example is using what's called a traveling wave parametric amplifier. Basically, this is a very long meandering feed line with engineered dielectric constant. With engineered the dispersion relation along the line. So you have you use the nonlinear kinetic inductance effect along the line to create sidebands from the pumping tone and use that to create gain and achieve quantum limited noise. So this is we just got a device provided by Peter Day from JPL, and we will test it out soon. All that comes to the conclusion. There's a lot that talk about. I won't go through all of them, but just to say, this is a really exciting and closely related field to QIS. There's a lot to learn from it, and we all care a lot about the phonons. I want to use phonon engineering to improve both the detector and the quantum sensing. Yeah, thanks.
Let's thank Xinran for a very nice talk. And are there questions or comments from the audience?
Hey, Xinran, thank you for the talk. I'm Ravi Nayak. So you looked into a number of different of these detectors and did some photon engineering in terms of these lattices that you're using to create these band gaps. Have you looked into the substrates themselves? Have you looked into if certain substrates are more favorable for this? I know there's a little bit of work done in qubits on using different substrates like high purity silicon or sapphire, but I don't know what your investigation is.
Yes. So for us, the substrate is the target. So we motivate ourselves from the physics side, like we are looking for the target that's coupled stronger to dark matter. Of course, sapphire is natural. It's actually a good choice for dark matter detection as well. And we do want to try with sapphire substrate. Yeah.
And in terms of the substrate as well, just follow up. How much does like the thickness of the substrate play a role? Like, is there a limit where you get to a place where you can squeeze out all the phonons and then just leave a little bit? Like, there's a certain thickness that's critical there?
Yeah. Right now we are working with a 1 millimeter thick substrate, and we do want some certain mass for the target. So for example, in this bulky example, they are actually using a 1 centimeter thick wafer. This is crazily thick, but we cannot afford to go very thin. Otherwise, we don't have enough mass to detect dark matter.
I see. Thank you.
Yeah.
Okay, other questions, comments? Okay, let's thank Xinran again. Thank you very much. It was a very nice talk.
Thank you.